Hello community, welcome to part B of multi-agent devices. Come back and focus here on a particular research I want to show you, and this is by Carnegie Mellon University. Some beautiful ideas here, published 6th of June 2024. Multi-agent imitation learning. Value optimization is easy. Regret gap minimization is hard. So those researchers here, some beautiful ideas, and this will be here, the content here going forward. So our agents. Now, you know, agents can be intelligent or not so intelligent, and in case one, we have the not so strategic agents. And what you mean? This is simply we reduce our multi-agent imitation learning problem to a single agent imitation problem over joint policies. How is this done? We drive the value gap to 0, so we achieve here the value equivalence. Simply that all AI agents in our environment that work together blindly follow the recommendations by the central intelligence, by the mediator, by the mastermind, whatever you want to call it. So this is of course not able to find new solutions to new emerging problems. This is just, we know what happened in the past and we can replicate past solution. That's it. No learning happening. Non-strategic agents. And you know there's another class, and it is the strategic agents. They are as clever as could be. Now we have agency that we need to account for the fact that agents may deviate in their policy from the recommendation policy, if it appears beneficial to do so from their own subjective perspective of an AI agent. So, time to take a step back and say, okay, where are we? So we are now introducing strategic agents in MAIL in our multi-agent imitation learning environment, where each agent has the ability to make independent decisions. They have agency and they may choose to follow or deviate from recommendations provided by a mediator or whatever you call the central guiding entity. The master AI, GPT 5, 6, 12, whatever. But with the implementation of the new idea of the regret gap, this will help us understand and measure the incentives for agents to follow or to deviate from those recommendations by this mediator. And as I already indicated to you, the strategic deviations phi I. To be absolutely clear, what is the definition? So for each agent I, the class of the deviation represent all possible ways in which the agent can modify its policy. And this deviation allows the agent to choose an action different from the mediator's recommendation if the agent believes it will achieve a better outcome, and it learns this simple by trial and error. The regretting used by the mediator's policy sigma quantifies the maximum potential gain an agent could achieve by deviating from the recommended actions. And you know, this is our simple difference, and this is our mathematical definition. You know, sigma is the mediator's policy, I is the index for all our agents, ranging from 1 to m. M is the total number of agents in our environment. Phi I represents the strategic deviation for a particular agent I. Pi sigma is the joint policy where all the agents follow the mediator's recommendation. Pi sigma phi I is not a joint policy where the agent I deviates according to phi I, while all the other agents follow the mediator's policy. And J of pi is the performance measure, the cumulative reward of an agent I under the policy pi. Take a minute, think about it. I needed to take a piece of paper, write it down, again, make some drawings, till I had an idea what it could mean. So this interpretation is now important. This difference, this term here now, represents the gain or the regret for an agent I by deviating from the mediator's recommendation. And this regret R, phi of sigma, is now the maximum possible regret across all agent and all possible deviations. So you're seeing we have here 2 times the max. And you know this is gonna be easy to compute. We just need compute power. Come now to the most important fact, the regret gap itself. What is it? It compares now the expert policy and the learner policies. And to understand the efficacy of the learn policy relative to the expert policy, the researchers introduced of the publication I showed you here the concept of the regret gap. So we have the regret for the expert policy, the R theta sigma expert. This is computed in the same way as R phi sigma, but using now the expert policy sigma e instead of the learner's policy sigma. So here we have it. This is our regret gap. Again, this is simply the difference. And this is now the metric that compares the regret induced by the learned policy sigma with the regret induced by the expert policy sigma expert. And what we have to do now is to drive the regret gap to zero. This is our optimization topic. And if we achieve that the regret gap comes to zero, or the regret equivalence, this means that the learned policy is as good as the expert policy in terms of the maximum incentive for any agent to deviate. Practically, this implies that an agent would have no more incentive to deviate from the learned policy than they would from the expert policy. And of course, whenever we do with Markov game, we need an equilibrium. And you know, in the simplest case, we have a Nash equilibrium, but here we have a little bit more complicated equilibrium, and it's called the correlated equilibrium in our multi-agent imitation learning with a mediator system. So this provides now a framework for understanding the strategic interplay between the agents within a Markov game. Beautiful. Okay, so we have here all our crazy educated agents. We have one mediator, one equal to all the others, and then we have to find a correlated equilibrium, and it is the main task of the mediator to find a stable system. Now you know that we have the potential that all our agents have now the power to deviate from the policy recommendation by the mediator. And now let the game begin. Correlated equilibrium. What is it? What is our elements? How we apply it? How does it work? Now you know we have key concept again, the strategy deviation. Now you notice the deviation set, the aggregated deviation, and all the induced joint policies. For my green grasshoppers, here you have them again in detail. Now we have the concept of a correlated equilibrium in male. So this means now a correlated equilibrium in the context of a defined Markov game with a mediator is defined with respect to the potential regrets associated with the deviation from the mediator's recommendations. This means, hey, we have a system with a lot of crazy agents. We have now some recommendation from the central intelligence agent we call a mediator, but each and every agent has also a pool of creativity that it can choose actions from to deviate from this official mediator's recommendation, maybe to find more intelligent, more faster, more secure solutions. Okay, so the regret of the mediator policy, or theta of sigma, calculated here. Now you know this formula, and we have an epsilon approximate correlated equilibrium. The condition is that the mediator's policy sigma is said to induce an epsilon approximate correlated equilibrium if the regret R phi sigma does not exceed epsilon. So this means in such a defined equilibrium state, no agent has a significant incentive that is greater than our epsilon to unilateral deviate from the mediator's recommendation, suggesting that the policy is nearly optimal in terms of coordinating agent actions toward the common goal. Beautiful. We just have to code this and then it is done. Great. Okay, let's take here one for my green grasshoppers. Very short summary. Pause here, think again, read the publication, talk to your GPT-4 or 5 system or Claude 4 or 5, whatever you have whenever you see this video. Short break. For my green grasshoppers, understand the mediator's role here in the strategy coordination of our bunch of intelligent AI agents in a common environment. A mediator in a multi-agent system functions to harmonize the actions among all the agents towards a common goal. It's not that everybody is doing just what it wants to do for its own sake, but you have a common goal, and it is the job of the mediator to bring harmony into all the deviations. This role is critical in ensuring that the actions of the individual agents are not only aligned, but also optimized for the collective performance. Remember from Star Trek the Borg with the Borg Cubus? Think about this. Now, the mediator does this by recommending actions to each agent based on the current state of the complete system of the environment, thus attempting to create a correlated equilibrium, where the recommended strategy is optimal now for the group as a whole. This is the job of the mediator. So we need here a real powerful AI system, or we need a different architecture for a lot of very intelligent little AI agents. But now for the moment we go with a mediator, because this is mathematically simpler to solve, to code, to implement. Key insight: the mediator's effectiveness is crucial in maintaining a strategic harmony and minimizing the potential for disruptive unilateral deviation by the agents. Sounds simple. Linking now the strategic coordination to a specific performance metric is a little bit more tricky. Okay, you know we have two measures. We have the value gap, the classical value gap, and we have the regret gap. And this regret gap measures now the maximum improvements any single agent could achieve by deviating, by not following the mediator's recommendations. So this captures here the incentive for each and every single agent to defect from the collective strategy, but just a little bit of an epsilon, which can of course undermine the system stability and efficiency, but we have to take care about this in coding. So we have now, if you want, a double effective optimization problem, because we have a value gap that focuses here on a collective efficiency, but this is not enough. If we want to have little intelligent agents that roll around, a little Speedy Gonzales and try all and everything in their available action space for themselves, but with a focus to have here a common good graded for each and every agent for the whole system, then we need the regret gap, and this here focuses on the individual incentive and on the robustness of the collective strategy against self-interested actions by our single agent's eye. Third point, practical implications and policy adjustments. Okay, in mathematical term it is easy. We have to minimize the value gap and we have to minimize the regret gap. And I show you the code in a minute. So, we have to understand that to reduce the regret gap, the strategies might involve making the collective benefits more apparent or rewarding to the agents. Or how do we teach those agents how to behave? Or tweaking the recommendation algorithm to better account for individual preferences or individual strategic thinking. And now then, malice and blade will come into a later point, and this is here the beauty of the system. So what is the key insight? Bridging here the theoretical and practical aspects involves some continuous refinement of the mediator strategy based on the performance feedback measured by the value and regret gap structures. Beautiful. Okay, I'm tempted to make here a break now for part 1 of this video, but let's see if maybe we go on for just one more thing. The main insight of Carnegie Mellon researcher was this. This research shows us a surprising result. The value equivalence, the first metric, does not directly imply a lower regret gap. Because in the worst case, they found, and there's a beautiful mathematical proof over several pages in the original literature, that they prove mathematically to you that the value equivalence fails to provide any meaningful guarantees to the regret gap. And this is now important because this is not happening in a single action imitation learning theory. This is now a critical distinction if you go from single agent to multi-agent. And this was not addressed here in prior scientific publication by other teams. Now you understand why from the very beginning of this video, I focused here on both metrics, the value equivalence and the regret equivalence. In the single case, the value equivalence was all we needed. But hey, we need complex multi-agent system. And now we have to optimize on a higher complexity level in addition to the value equivalence. I told you, it is easy if you understand it. So for my green grasshoppers here, I looked for a simple explanation of the regret gap. If you encounter this the first time, maybe it is a little bit much. So, the regret gap in the context of a multi-agent imitation learning matches here the largest possible improvement in performance that any single agent could achieve by choosing to deviate from the recommended actions by our mediator, or the strategy provided by the system, either the mediator or a learned policy. So essentially, it quantifies now the temptation an agent has to ignore to advise, given, and act on its own. Think about this. Imagine a team of players, each given a playbook by their coach. The coach is the mediator, the central intelligence. If one player discovers that they can score more points in the game by deviating from the playbook in certain situation, the regret gap is the difference in points they could gain by following their own plan of the players versus sticking to the coach instruction. As simple as this. This is the regret gap. And this is a continuous improvement process. And why do we measure here the regret gap in mail? We want to have a stable system. We want to have stability of our strategies. And the regret gap helps to ensure that the strategies or the recommendations are stable, not just short term, but also in the medium and long term run. So this means that no single agent can significantly improve their outcome by acting differently from the overall strategy. And this reduces the likelihood of agents deviating and ensures a consistent adherence to the plan, making now the system more predictable and reliable. But of course, we want also to have an optimization of the collective performance. So in many multi-agent settings, the goal is not just to optimize the outcome for individual agents, but to maximize the overall performance of the system. And interestingly, by minimizing here again this regret gap, you encourage the cooperation between the agents. They won't have much to gain by going crazy, which often leads to better outcomes for the group as a whole. And by minimizing the regret gap, you encourage cooperation because agents won't have much to gain by going rouge, by going yippee, which often leads to a better outcome for the group as a whole. Okay, anything else? Yes, of course. They are more robust to changes in the environment or the agent behavior. They are less sensitive to the potentially disruptive actions by any one of the agents, as the incentive to deviate are now minimized. And a robustness is crucial in dynamic and complex environments like the financial market or cyber defense. Why we have to deal with all these deviations? Why, you might ask? Again, the idea behind all of this is to allow slight deviation from the historical known expert policies in multi-agent imitation learning. And we have one goal, and this is to explore new strategies or new paths that could potentially improve the outcome or adapt better to new, evolving, varying conditions that are not covered by the expert demonstrations. And you know exactly where we are going to. So this exploration is now crucial because it can uncover valuable insight that were not evident and not available in the original expert data. So just analyzing historical financial patterns in huge financial transaction data is not the way forward. Great. Yeah. Okay, I told you there are two new beautiful algorithms, and they are now here, and we start with the first one, and it is Malice. But of course, Malice is based on Alice. You say, of course, what else? So what is it? Alice is now a methodology in imitation learning that addresses the issue of distribution mismatch between the expert demonstration and the learner's policy. And this damn mismatch can lead to significant learning errors due to, and you notice, the covariate shift. And this is a scenario where the condition under which the model was trained now differs from those conditions under which the new model is tested or the model is now applied in the real-world scenario. You know distribution mismatch, or at least you know covariate shift. And this is here the publication if you want to understand it. And we have Princeton and Carnegie Mellon. This is February 11, 2021, the latest version of this paper. Feedback in imitation learning, the three regimes of covariate shift. And of course, we only go for the most advanced at the time. And this is Alice. Now, okay, I should come to an end. But covariates for my green grasshoppers, if you're not familiar with this, never mind. It is easy. In machine learning context, and this is specific to ML, covariates refer here to independent variables or predictors that are used to model or predict an outcome of the system. So in essence, covariates are the input features that influence or are associated with the dependent variables, the outcome in an analysis or the model. Covariates are typically the variables that the researchers or the algorithms use to build predictive models, aiming to explain or predict outcomes based on the variation in these features. So, imitation learning, covariates would be the features of the environment or the agent state that will influence the decision making, such as the position of obstacles in our traffic example, the speed of movement, or the proximity to a goal. Covariates are known for a long time. Talk to your GPT-4 or 5 system. Dig in. There's some broad historical knowledge about this. The distribution mismatch that is happening now on our complexity level is now different from the covariate shift. And this is a mistake a lot of people make. They think that the distribution mismatch now is identical to the covariate shift happening here. Unfortunately, the complexity increased. So, the distribution mismatch between the expert demonstration and the learner's policy, a common challenge in both single-agent and multi-agent imitation learning, arises primarily due to the nature of how the learning and the decision-making environments change, evolve over time. Okay, in the multi-imitation learning, like with Malice we're going to encounter in a minute, the concept of a distribution shift broadens now. It still encompasses here the traditional covariate shift that you know from 2021, sorry. It still encompasses here the traditional covariate shift between the expert and the learner state distribution. But crucial now in our improved complexity, it also includes now the shift induced by the potential agent deviations, all of them. So this means the strategic nature of the agent mean that they might deliberately take actions that deviate from the expert recommendation, leading to a state disruption that are not explicitly covered by the expert demonstration. And this is a unique challenge in multi-agent setting. You know all of this, but you have to remember, we are now not talking anymore about a simple covariate shift, but about a distribution mismatch. Now, if you really want to dig deep into this, here are 6 key reasons for this mismatch. Initially, the learner's policy is often far from the optimal because it starts with limited knowledge about the environment. And as the learner policy evolves through its training, it naturally diverges from the state action distribution of the expert demonstration simply because the learner is still trying to approximate here the expert decision and strategies. Second, you know the good old game from exploration versus exploitation. Exploration involves taking actions that deviate from those observed in expert demonstration to discover potentially better strategy or to learn more about less understood areas of their particular state space. Now we have this beautiful divergence in the action choices. This exploration that is setting in now leads to visiting states or taking action that may not align with the expert choices. But since we are now visiting new state and action space that is possible and open to us, it starts now to create a different distribution of experience, state, and action pairs. But this is what we want. Then, of course, we have the classical covariate shift. As the learner interacts with the environment, the conditions under which the decisions are made can shift. The covariate shift, happens because the learner's presence and decisions alter the environment dynamically with a feedback, affecting the distribution of the states it experiences compared to those in the static expert datasets. So the action taken by the learner can influence the future states differently than action taken by the expert, leading here to these complicated feedback loops that further diverge the learner's experience from the expert's experience. 4. Compounding errors in the sequential decision making. Errors that happen very early in our decision chain propagate over time, leading the learner to entirely different parts of the state space to explore than those that are commonly visited by the expert. So, the learner has now developed or discovered new areas in its available state space that were never visited by the expert themselves. So this divergence now is compounded over time, especially in complex environments where the action have long-term consequences. And if we have an error at the very beginning, my goodness, this error propagates. 5. Incomplete or non-representative expert demonstration. Now that we learned that there are state spaces that an expert might have never discovered and is not available in the training data set for the learner, this is it. So expert demonstration may not cover all possible state in the complete action space or the state space or scenarios, particularly those that are rare or emerge only under specific conditions that were not encountered or recorded by the experts. But the learner now finds those lost spaces. So expert data might be biased towards certain strategies or solutions that work well for specific scenarios, but are not universally optimal across all possible conditions. Wow. 6. Okay, we have this, the last one. Inter-agent effects. If you really want to be down to the bottom of this, in multi-agent system, the action of other agents, whether cooperative or competitive or neutral, can significantly alter the state space from what was seen in the expert demonstration. Because we are in a dynamic evolving system. So each agent strategy affects the others, leading now to a more complex, more dynamically changing environment, challenging environment, where the collective behavior can diverge significantly from that observed in the training data. Isn't that beautiful? We have a dynamic in the system that we were dreaming of. But now we have to handle this almost chaos when coding it. So this is why we really have to understand what we are doing. Otherwise, you will sit in front of a code and it will just go crazy. Okay, for my green grasshoppers. Okay. I was talking about a distribution, and I know that this question will come in this video. So in imitation learning, if I say about distribution, what exactly do I mean with a distribution? distributions are. So in imitation learning, and we are just talking about imitation learning and maybe a little bit about reinforcement learning, a distribution refers to the statistical properties that describe how the data is spread or distributed across different variables or states. So more specifically, when talking about training a learner, a student AI model, under one distribution and testing it under another distribution, like the real-world distribution, we're now discussing the differences in the frequencies and the types of data or scenarios that the learner encounters during training versus those it faces in the real-world application or during evaluation. So let's break this down into digestible components. I called it beautiful. The distribution in the learning environment, we have state distribution, we have action distribution, and we have state action distribution that you have to take care of in your code. State distribution. This refers to the probability of encountering various states in the environment. In reinforcement learning and in IL, a state represents a specific situation or condition of the environment. For instance, in a driving simulation, a state could describe here all visible cars, the position, the speed, the direction, different vectors of acceleration, whatever. Action distribution. This covers the range and probability of action taken in different stages. For example, the action distribution in a game might show a preference for certain moves or certain strategies depending on the game's state. And state action distribution, this is a combination of both state and action distribution, and it describes the probability of encountering particular states and taking specific action in those states. So this distribution is crucial in learning the policies that will dictate the action a specific agent should take in each specific state. Okay, my little green grasshoppers, I feel you. Second, the training distribution. So this is now derived from the expert demonstration set. So in imitation learning, the training distribution is typically derived from expert demonstration. You know this. It includes the state the expert encountered and the actions the expert chose in those states. And that this distribution can be limited by the expert's own experience, and it might not cover all potential scenarios the learner might face. And this is the problem, and this is why we need deviations. And there's no place for absolute, yes, I will only follow what my expert tells me. You have to be creative your own. Biases and limitations. The training data might be biased towards more common or some familiar scenarios, and it might not include the rare but critical situation. Think about CrowdStrike Microsoft outage. For example, in the autonomous vehicle training, the expert data might predominantly include driving in clear, dry condition, and maybe not in foggy or icy conditions. But you have to integrate this in your training dataset. Third, the testing or the operational distribution. This distribution includes the state and the action that the model encounters when deployed in the real-world setting or during the simulated testing phase. This can be different from the training distribution if the real-world scenarios include elements or combinations that are not covered by the training data. Especially in dynamic or complex environment like in our financial markets or in weather systems or interactive games, the operational distribution can vary greatly over time and might include scenarios that were not part at all of the training dataset. And you have to take care about this, and I will show you how we do this. Overfitting and performance issues. Overfitting, you know this. This occurs when a learner is too closely fitted to the training distribution alone, including all the noise and the specific that are not generally applicable. It excels on the training data, but on the training data alone, and it performs poorly on data not seen during training, like say in the real-world scenario. And if a learner has only seen examples from a narrow set of conditions, beautiful sunshine, it might not perform well under different conditions that appear in operational distributions. If you have here AI that controls here multiple robotic arms, and you have a different distribution of light sources in the room, and you have different form of shadows, this causes significant problems. And this is a significant deviation. And here you have completely different distributions. Okay. So in summary, my little green grasshoppers, the distribution in the learning context refers to how data, state, and actions is spread out and the likelihood of encountering specific data points. And we have to ensure that the training distribution aligns well with the operational distribution, and this is key to develop a robust and generalizable AI system for real-world application, and this is damn complicated. So this alignment challenge here now addresses through various strategies, include diversifying the training data, simulate rare scenarios, and continuously updating the model with new data from the field. This is what we have to integrate in our code. So you might ask now, hey, if I think about your last video about this visual model with a robotic arm and a camera mounted here real close on top of the arm, and you have the different in the light, and you have the different in shadows, and you have different viewing angles. All these are now different distribution. Yeah, exactly. If you have a robotic arm, like I showed you in my last video with a camera, all those variation, different lighting conditions, different shadows, different viewing angles, they all represent different distribution. So what we do, for example, camera angle is easy. You have now training data with a camera angle of 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees. All of this must be in the training data, otherwise our AI system is lost. Implications now for the robotic control system of my last video. This augmentation, this syntactic augmentation I showed you, and this computer simulation, this CAD system that we use now to generate syntactic training data, now you understand why. Because we have to have those syntactic training data available for our AI algorithms to be trained on. Different light sources, different shadow, modified angle. All of this needs to go into training data and needs to be fed into the continuous learning cycle. Okay. I told you Alice. Yeah, okay. Now it's officially time to end this video. I feel it's above 10 minutes. So in part 2 of this video, we're going to look at this. Please have a look at this publication if you want to read a little bit in advance. Alice. Have a look at the Alice model, because we will use Alice in part 2 to come to Malice, and a beautiful improved algorithm for multi-agent imitation learning that will work beautifully. This was it for part 1. I hope you enjoyed it. I hope you learned a little bit. I hope you found it fascinating. I hope you found new ideas. And it would be great to see you in my next video.